Okay, so for the RL low pass filter, you're going to see that the process is virtually the same. Now we're going to use the relationship for inductive reactance. We're going to convert manipulate the formula a little bit here, but the process you'll see is the same. So this is going to be a pretty quick process to get us through the RL low pass. So a basic RL low pass filter shown on the right there. Notice that the output voltage again is taken across the resistor this time. You would have thought it would have been across the inductor, but no, we're going to take the output across the resistor because the characteristics are different. When the input is 0 or DC, the output voltage ideally equals the input voltage because X sub L is a short if the winding resistances are neglected. Okay, so we have to put that caveat in there. As the input frequency then is increased, X sub L increases, and as a result, the output, V out, gradually decreases until the critical frequency is reached. At this point, X sub L then is equal to R, just like we saw with the previous X sub C equal to R. And the frequency is, so we go through our manipulation. Basically, we start off with our relationship for X sub L. In this case, we're going to set 2 pi, the critical frequency times the inductance, equal to the pure resistance. So the critical frequency then can be solved by using the relationship R divided by 2 pi L. And in this case, we're going to move the resistance out of the numerator into the denominator so that the critical frequency then is equal to 1 over 2 pi L divided by R. So just as in the RC low pass filter, the output then is again 0.707 times the input voltage, and thus the output voltage is negative 3 dB below the input voltage at the critical frequency. So if we look at trying to solve a problem here, we've got again a 4.7 millihenry inductor, 2.2 k ohm resistor. The critical frequency then can be solved for by inserting the values of the inductor and the resistor into the relationship 1 over 2 pi 4.7 millihenries divided by 2.2 k ohms, and we get a critical frequency of 74.5 kHz. So that's where our transition then will be placed on the Bode plot that you can see in the lower right. Again, the red line is the ideal response, the blue line is the actual response. The output then is flat or below the critical frequency of 74.7 kHz, so you mark that on the semi-log paper at 0 dB. At that point, things start to change. And so as the frequency is increased above the critical frequency, the output drops to minus 20 dB per decade. Thus, as the ideal curve, every time the frequency is increased by 10, the output is reduced by 20 dB. A slight variation from this occurs in actual practice, but the output is actually at minus 3 dB rather than 0. So you can see the actual curve, it's down minus 3 dB, but on our Bode plot, we just plot it at the line. So we look at then something called the phase shift in a low pass filter. The RC low pass filter acts as a lag circuit. Recall from chapter 15 that the phase shift from input to output then is expressed as minus the inverse tangent of R over X sub C. At the critical frequency, again, X sub C is equal to R, and therefore the phase angle then is minus 45 degrees. As the input frequency is reduced, phi decreases and approaches 0 degrees when the frequency approaches it. In the figure, we can see that we have a phase characteristic that happens then. So you can look at either one of these. If we look over here, F sub C, then we can see that we have a shift occurring 0 to minus 45, minus 45 to 90. The RL low pass filter acts like a lag circuit. Recall from chapter 16, the phase shift is expressed again as the minus inverse tangent, but this time we have x sub L over R. In the RC filter, then, the phase shift from input to output is that minus 45 degrees at the critical frequency and decreases for frequencies below the critical frequency. So the next section we're going to take a look at is high pass filters. So we've looked at low pass filters. Next we move to high pass.